Okay, this is kind of old school, but if you guys remember in the 180 series, we played with this Phet simulation called charges and fields. And the reason why I want to pull it up now is that it is a really easy, nice way to conceptually view the electric field and also what we're going to introduce next, which is called voltage. Okay, so right now what I have is the electric field plotted. It's not plotting the actual, these aren't really vectors. They're just showing the direction, not the actual intensity. The intensity is shown by the color scale, basically the gray scale. The reason for that is the intensity of the electric field decreases rapidly far away from the charge. So as I showed you with Mathematica, it's actually hard to get a nice vector field of the electric field, okay? But if I look through here, now I can put a sensor, and this will show me, right, how the strength of the electric field changes. I've got a bunch of different charges here, and the fields of these individual charges are superimposed. What we've proven through using this idea of curl and the fundamental theorem of curl, or Stokes' law, is that everywhere I calculate the curl, if I imagine putting a paddle wheel anywhere in this electric field, which is this complicated electric field that is the superposition of a bunch of different charges, I would find that the curl is zero as long as these electric fields are static, okay? So the curl is going to be zero everywhere. If I calculated the divergence of the field would be related to the charge density. Okay, so everywhere where there isn't a charge density away from the charges, I would find that the divergence is zero. When I got on top of these charges or on an actual charged surface that has a non-zero charge density, I would find that the divergence would not be zero. Okay, and that's where I want to bring in that delta function. What we're going to talk about next is something called voltage. And I really like the way the sim shows voltage with these colors. So I'm going to get rid of our electric field. And now kind of the intensity of the light is giving you a measure of the voltage, which is also called the potential. Okay, and you can measure the potential in units of volts. And you can see here that this thing that we call potential in this simulation, it's negative near the negative charges. If I put it near the positive charges, I get a positive value for the potential. If I move it really far away from any charge at all, it starts to drop down to small values. And I'm going to argue that it's usually defined to be zero well away from the charges or at a distance of infinity. Another nice thing you can do with this sim is plot what is called equal potential lines or equipotentials. So these are lines where the potential is equal all along them. Okay. And actually, I'm going to erase them all. There we go. And what I want to do actually before I do anything else, I'm going to plot them at roughly. And if you do see a map of equipotentials, that is typically what is done. These equipotential lines in terms of learning something from them are kind of useless unless you diagram them at equal intervals. So now I have all of these particular potential lines. They're spaced out by about 5 volts. Okay, so I want you to think about when you're looking at this, these equipotential lines, when you look at it in a map like this, they're a lot like topographic lines on a topo map. So on a topo map, if you've got a couple of topo lines that are very close together, like this, that indicates a very steep slope. Okay, steep slope. Okay, if they're far apart, topo lines on a map, that indicates that the slope is changing more gradually. So you can think about how this is related to equipotential lines and the electric field. If I put it here where the equipotential lines are very close together, okay, this means there's a rapid change in the potential over a very small distance. And we get a big, strong field that's indicated by this long arrow. If I instead put it over here, where the same change in potential occurs over a larger distance, then you get a much weaker field. Okay, same thing here and here. And if I look over here, and then notice that the electric field line is always perpendicular to the equipotential line. Okay, so I don't want to talk about this in too much detail, but I would encourage you guys, as we're learning about potential, open this sim and explore it a little bit and just think deeply about it and make sure you have a good visual understanding of the relationship between these potential lines, okay, equipotential lines, and the electric field.